And now we move on to the final unit in this course, discussing the order of integers. As always, when we start a new unit, we do need to introduce a few new definitions. Suppose n is a positive integer and a is relatively prime to that integer. Euler's theorem tells us that a to the phi of n will always be equivalent to 1 modulo n. In other words, there are at least some positive integers k, so that a to the k is equivalent to 1 mod n. Phi of n is one such integer, but there might be more. So we define, for this positive integer n and a relatively prime to it, the order of a modulo n is the smallest positive integer that satisfies a to the k is equivalent to 1 modulo n. And we write this as order subscript n of a, and we just say it out loud as the order of a mod n. So from this definition, there are three observations we can make right away. The order has to be a positive integer because it's the smallest positive integer that solves this equivalence up here. So the order has to be positive, it's at least as big as 1. Since the order is a power of a equivalent to 1 mod n, if you raise a to that order, it's definitely going to be equivalent to 1 mod n. And finally, the order is the smallest power of a that you can raise a to and be equivalent to 1 mod n. Therefore, it can't be any larger than phi of n, because we already know a to the phi of n will be equivalent to 1 mod n. So it's a positive integer, somewhere in between 1 and phi of n, possibly equal to one of those two things. A raised to that power is equivalent to 1, and it's the smallest such integer. So think of it as the first positive power of a, which is equivalent to 1 mod n. So you start with a squared, a cubed, and so forth. We know eventually we're going to be equivalent to 1 because a to the phi of n will be equivalent to 1. So you just keep going down the list of powers of a, and the first time you see a 1, that's the order of a. So let's take a look at a few examples. Compute the order mod 12 of 7. Well, 7 to the first is not equivalent to 1 mod 12, but 7 squared is equivalent to 1 mod 12. Therefore, the first positive power of 7 equivalent to 1 mod 12 is the second power, so the order mod 12 of 7 is 2. Next, let's compute the order mod 13 of 4. So we just start computing powers of 4, and these are all reduced modulo 13. 4 to the first is equivalent to 4. 4 squared is 16, but that's equivalent to 3. Remember, we're working modulo 13 now. 4 cubed is 4 squared times 4. We've already computed that 4 squared is equivalent to 3. So 4 cubed is actually 3 times 4, which is 12. 4 to the fourth would be 4 cubed times 4, or 12 times 4. 48 modulo 3 is equivalent to 9. 4 to the fifth, we do 4 to the fourth times 4. 9 times 4, that's 36, but modulo 13, that's 10. 4 to the sixth, 4 to the fifth times 4, 10 times 4, 40, which mod 13 is 1. So the first time we saw a 1 in our list, powers of 4, was the sixth power, so the order mod 13 of 4 is 6. Compute the order mod 12 of 3. Well, 3 and 12 aren't even relatively prime, so this order isn't defined. It doesn't even exist. If you compute powers of 3 modulo 12, none of them will ever be equivalent to 1. Okay, let's continue making some observations about the order of integers. For any positive integer n, the order modulo n of 1 is just 1. The proof is pretty straightforward. 1 to the first is just 1 as an integer, so it's definitely equivalent to 1 mod n. So the first power of 1 is always equivalent to 1, therefore the order of 1 is always 1. Next, for any n 3 or larger, the order of -1 is 2. -1 squared is definitely equal to 1 as an integer and therefore equivalent to 1 mod n for any n. But in order to conclude that the order is equal to 2, we need to know that that's the first power of -1, which is equivalent to 1 modulo n. It's not just enough for -1 squared to be equivalent to 1. We need to know that -1 to the first isn't. So the only power before the second power to worry about is the first power. Is it possible for -1 to the first to actually be equivalent to 1 modulo n? If so, then n has to be a factor of 2. In other words, n is either 1 or 2. So as long as n is not 1 or 2, -1 to the first is not equivalent to 1 mod n, Therefore, once n is 3 or larger, since negative 1 to the first is not equivalent to 1, but negative 1 squared is, the first power of negative 1 equivalent to 1 modulo n would be the second power. So as long as n is bigger than or equal to 3, the order modulo n of negative 1 is 2. Observe we have seen that modulo 2, the order of negative 1 is 1. We're now primed to make a very useful observation. Suppose n is a positive integer and a is relatively prime to it, as before. I and j are two integers. They're not both 0, but a to the I and a to the j are both equivalent to 1 modulo n. Well then, a raised to the greatest common divisor of those two exponents will also be equivalent to 1 mod n. By Bézout's identity, there must be two integers x and y, so that ix plus jy is just equal to this greatest common divisor. But a to the I was equivalent to 1 mod n. A to the ix is just a to the I to the x. Since a to the I was equivalent to 1, that's just 1 to the x, in other words, 1 mod n. Similarly, a to the jy is going to be equivalent to 1 mod n. I can take the product of those two things. On the one hand, a to the ix times a to the jy, but on the other, 1 times 1, because a to the ix was equivalent to 1, and so was a to the jy. On the left, we take the sum of the two exponents, and we get a to the ix plus jy is equivalent to 1 mod n. But remember, ix plus jy was exactly equal to the GCD of I and j. So a raised to that GCD will be equivalent to 1 modulo n. The real point of this theorem is the following corollary. The order modulo n of a must be a factor of phi of n. So we have two things. By Euler's theorem, a to the phi of n is equivalent to 1 mod n. However, a to the order modulo n of a is also equivalent to 1. That's just part of the definition of being the order mod n of a. Using the above theorem, since I have two powers of a, both of which are equivalent to 1 mod a, they're not both 0, in fact they're both positive. A raised to the GCD of those two numbers must also be equivalent to 1 mod a. Now the order mod n of a is the smallest positive power of a, so that a to a power is equivalent to 1. So the smallest positive power, so that a to this power is equivalent to 1, cannot be any larger than one particular power, so that a to that power is equivalent to 1. This GCD is a power of a, equivalent to 1. This is the smallest positive power of a, equivalent to 1. So the smallest one is less than or equal to one of them. However, we can also say the GCD of two numbers is a factor of both of them. So whatever this factor, this greatest common factor here is, it is a factor of the order of a. They're all positive numbers, so the factor is less than or equal to the positive number it's a factor of. Therefore, since we have the order is less than or equal to this GCD, but it's also bigger than or equal to it, they must be equal. So the order is this GCD, but this GCD is a factor of phi of n. Therefore, since this GCD is the order is a factor of phi of n, and that was what we were setting out to prove. So the point of this is that we know the order mod n of a is less than or equal to phi of n. We established that a while ago. But of all the numbers that are less than or equal to phi of n, 1, 2, 3, all the way up to phi of n, they couldn't all be the order. The order mod n of a has to be a factor of phi of n. There's another pretty quick useful result that we can state now. Suppose you have a positive power of a, which is equivalent to 1. That power, k, has to be a multiple of the order. In other words, the only positive powers of a that are going to be equivalent to 1 modulo n will be multiples of the order. Well, from the previous slide, if a to the k is equivalent to 1, and certainly a to its order is equivalent to 1, well then a raised to this greatest common factor is equivalent to 1. Of course, the greatest common factor of two numbers is a factor of each of them, so it's a factor of the order of a. But since the order of a is the first positive power of a equivalent to 1 mod n, we can also claim that that number, since it is a particular power of a, equivalent to 1 mod n, must be bigger than or equal to the order, the first positive power of a, equivalent to 1 mod n. The only positive factor of the order, which is at least as large as the order itself, is the order. Therefore, the greatest common factor of k and the order is the order. And again, Whatever this number is, it's the greatest common factor of these two. So whatever this number is, it's a factor of k. But this number is the order. Therefore, the order is a factor of k. Very similar reasoning to the previous slide. All right, we continue with n a positive integer and a relatively prime to it. For convenience, I'm going to say that the order mod n of a is the number k. Then suppose you have two positive numbers, I and j. So they're at least as large as 1. They're no bigger than k, and they're not equal to each other. So I have two different numbers somewhere in between 1 and k. Since they're not equal to one another, one of them is smaller than the other. I'm just calling I the smaller one and j the bigger one. So if I have two such powers of a, they cannot be equivalent to each other mod n. Why not? Let's suppose I and j are two integers. They're positive. They're no larger than k. I is the smaller one. However, a to the I is equivalent to a to the j mod n. A was relatively prime to n, which means every power of it is as well. So a to the I is relatively prime to n. Therefore, there is some y that is its inverse, mod n. If I multiply both sides by y, well, what's y times a to the I? Since y was the inverse of a to the I, it's just going to be 1. But that's just a to the negative I. Therefore, on the right, I can call this a to the j minus I. So I, remember, was less than j. I assumed I was the smaller of the two. So this exponent is positive. So now I have a to a positive exponent equivalent to 1 mod n. The order was called k. That's the smallest positive power that satisfies that property. So this particular power can't be any smaller than the smallest positive power that satisfies that property. However, I and j are in between 1 and k. The biggest j can be is k, the smallest I can be is 1. So the largest that j minus a can be is in fact k minus 1. So j minus I is less than or equal to k minus 1, so it can't be bigger than or equal to k. So since both of these powers were specifically in between 1 and k, I can't have this. Therefore, these two powers couldn't have in fact been equivalent modulo n. So in other words, any two powers of a, up to and including the order, a to the first, a to the second, all the way up to a to its order, cannot be equivalent modulo n. So if I list those things out, a to the first up through a to its order, those are all different modulo n. What happens if I go past the order? Well, a to the order plus m could just be factored as a to the order times a to the m, but a to its order is definitely equivalent to 1. So what that says is if I start listing powers of a larger than the order, so order plus something, I'm just going to get a to that thing I added on. In other words, a value I'd already seen as I was listing them out. So if I list out the positive powers of a from the first to its order, those are all distinct modulo n, but also they're the only values that any power of a can take modulo n. If I keep going for higher and higher positive powers, I'm not seeing anything new. So let's take a look at an example. List out all the powers of 2 modulo 7. We're just going to compute powers of 2, reduce them mod 7. 2 to the first is 2, 2 to the second is 4, 2 to the cubed is 8, but that's equivalent to 1 mod 7. Now that we've found the order of 2 is 3, because that was the first power of 2 equivalent to 1 mod 7, we've listed out positive powers of 2, and we've reached the order. Therefore, those are the only possible powers of 2 modulo 7. If we kept going, we would find, for example, that 2 to the fourth can be written as 2 cubed times 2 to the first, or 1 times 2, which is 2 again. 2 to the fifth is 2 cubed times 2 squared, or 1 times 4, so 4 again. 2 to the sixth is 2 cubed times 2 cubed, which is just 1 again. If I kept going, 2 to the seventh is now 2 to the sixth times 2 to the first, but 2 to the sixth was 1. So we see a value of 2 again. 2 to the 8th produces 4, 2 to the 9th produces 1, and so forth and so forth. If we keep going, we just see the values 2, 4, 1, 2, 4, 1, 2, 4, 1. Another example, let's list out all powers of 3 mod 7. 3 to the first is 3, 3 squared is 9, which is equivalent to 2. 3 cubed, I just have to take 3 squared and multiply it by 3, so 2 times 3 is 6. 3 to the 4th will be 6 times 3. That's 18, which modulo 7 is 4. 3 to the 5th will be 4 times 3. Note, all I'm doing is I'm taking the previous power of 3 and multiplying it by 3. So 3 to the 5th is 3 to the 4th times 3, so 4 times 3. 12, which mod 7 is 5. 3 to the 6th will be 3 to the 5th times 3. 5 times 3 is 15, which mod 7 is 1. Now that we have found the order, modulo 7 of 3 is 6. This was the first power of 3 equivalent to 1 mod 7. This list accounts for all possible values that the powers of 3 can take mod 7. 3, 2, 6, 4, 5, 1. If I kept going, they would just repeat this list over and over. But notice that's actually an entire reduced residue system modulo 7. It's the standard reduced residue system mod 7, just not written in increasing order. Therefore, the powers of 3 actually form all possible residue classes mod 7.